you will never end doing any of these. Now you can do for whatever purpose that you want, you can do it. Okay. Real and model. So this is a real microstructure. So I just want to show you some comparisons. This is a real microstructure, right? What are these particles? Not just unhydrated. Remember, this is only black and white, right? So this is black has to be the pores, white are all cement grains. This is in the fresh state before reaction, right? But really these are all different shapes. Like I said, computationally it will take a lot of time. So I'm assuming everything to be in the form of a sphere. And then if you have a real microstructure like that with the correlation function, your simulated microstructures are very similar. They're not exactly the same, but they are very similar, and you're okay. You can be okay with that. And then the other thing that you can also do is if I have one slice like this, again, there are I think, have you heard of a software called Aviso? So it's an expensive software, Aviso Fire. But that software does it, but you can write your own MATLAB programs to do it also, if you're good at MATLAB. So basically you take one image, you find the correlation function for that image. Remember the curve that I showed you yesterday? Correlation function where the value, so you basically throw in lines of different lengths, and when you throw a point, what you get is a porosity, and you see the curve plateauing off, the value at the plateau is the square of the porosity. You draw a tangent at the point of start, and where the tangent meets the asymptote, you come down, that's a critical length. You take the first derivative of the function with respect to that length, you get the 1/4 of specific surface area, right? We did that yesterday. Same idea here. So you take an image, you take that correlation function, use that correlation function and do some more manipulations, and then for the same image, basically what I'm telling the computer and telling the software is, say, here is my image, give me another 300 images where the porosity is very similar, the specific surface area is very similar, the pore size distribution is very similar, but the pore orientation is different. Is that not what you have when you take a piece of concrete and cut it into different layers and see? Is that what not you have? Right? If you take one layer, and if you have a reasonably representative structure, you typically have, I told you yesterday, as per stereology, the volume fraction in 2D will be equal to volume fraction in 3D, or area fraction in 2D will be equal to volume fraction in 2D. So basically, if I have one layer, and if I know how much is the porosity, what are the pore sizes, the next layer will have roughly the same characteristics, but the pores being in different locations and different shapes. So basically, what I'm telling the computer is trying to tell him, give me 300 more slides that are statistically the same as the slice that I gave you, but the randomness is different in all these slices. See that? You get the idea? So correlation function, the curve that I gave you is going to be exactly the same. Specific surface area is the same, porosity is the same, square of the porosity is the same, all of them same. All you have difference is the location and orientation of the pores. If you do that, then if I get 300 of them, I stack all those 300, they look like that, right? Now, from 2D, I have created a 3D structure. I mean, these are advanced, very advanced tools. You won't see too many people doing this in research, but the message I want to give you is the software that you want to use is not unavailable. SemHide 3D can give you slices. All you need is a MATLAB program to stack up the slices. MATLAB has a lot of, again, how many of you have used MATLAB? MATLAB has plenty of help videos and interfaces. You go, MATLAB has simplified mathematical computation to a point where you don't need a teacher. You don't need somebody to teach you that. All you need is interest. Of course, you need that. You can't say that, oh, I don't like computers. I don't like to do. A lot of civil engineers have seen this. Oh, I don't like to do calculations. I don't like to do computations. No, computations are your friend. You cannot just say that I will go to the lab and keep crushing concrete all the time. Right? There are enough people. Again, I keep telling this, right? There are enough technicians around to do those things. We don't need to train more technicians. They're there. We need to train engineers who can solve problems use these techniques to develop newer things. So if you are averse to doing computations, if you say that, oh man, I don't know math, computations are too complicated. No, look at MATLAB videos. There are a lot of scripts. MATLAB gives you a lot of these pre-packaged scripts where you can add your little components into it and clean it up. A lot of self-help. You can do that. It's not very hard. So you can start creating these microstructures. All of these are what my students developed. We don't use many commercial programs at all. We write pretty much every program that we want to use because I have complete control over what I write than what a company gives me, right? Mostly for finite elements, we use commercial software because it's too complicated to write finite element codes on our own. But we have written finite element codes on our own also for different purposes. But we do, for example, if you do some things that Abacus or ANSYS doesn't have, we do it on our own. But generally, these are things that will take a grad student, a PhD student who knows MATLAB a few months to do this. But it's well worth the effort. Because once you start automating this, it's only the initial time that it takes to get this automated. After that, you will be amazed by the speed of your research, right? You'll be amazed by the progress that you can make because the initial time is all that you will take to get this set up. Okay. Again, like I said, all the correlation functions have to be similar. You can see image 1 and through image 7, the correlation functions are broadly similar, right? All of them are very similar, so you get the images are statistically similar. We talked about this interface. You can do from the line parts, you can find the probability for the interface also. Again, the text is moving. You have 3-point correlation functions. You 1-point correlation function, which means you throw a point. 2-point correlation functions, you throw a line. 3-point correlation functions, you throw a triangle, right? Very simple. You throw a triangle or a combination of line segments of length r, s and t to a planar section, determining that the 3 ends lie in the same phase. So now here 1 end is in this phase, 2 ends are in this phase. Here 3 ends are in the same phase. So determining the probability that 3 ends lie in the same phase. Now, will a 2-point correlation probability be higher or a 3-point correlation probability be higher? If I have to have 2 ends lying in one phase higher or 3 ends lying in one phase higher? 2 will be higher, 3 will be lower. So the more the number of constraints that you put on, the lower the probability that you get. But different microstructures, you can use it for different purposes. Okay, so with that, we can go to the idea of percolation. And percolation is an important characteristic for any porous medium, not just concrete, but for any porous medium. And anything that you see as a contributor to deterioration of concrete starts as a percolation problem. Okay? Whether it's moisture going into concrete, whether it's chlorides going into concrete and corroding the steel, whether it's sulfates going in from the soil and creating sulfate attack and destroying the foundations, whether it's alkalis going in, all of these start with percolation. So whenever you talk about the pore structure, it's important to characterize the percolation threshold of that system. And I'll tell you what the importance is. It's an extremely important characteristic. Again, especially for those of you who are doing research, again, if you are a field guy trying to find out the durability of concrete, I wouldn't ask you to go and do percolation. You do all the standard tests and do it. But if you are a researcher trying to understand more of fundamentals, which many of you are, this becomes another important contributor. Okay. So percolation is a study of how systems of discrete objects are connected to each other. Now, have you noted how ants move from one end to the other? Have you watched ants move? Do they go in a straight line? Do they go in a straight line? Typically no, they kind of go around. They have some hormones that they are searching for and following that line because they know where the food is and all of that, right? But eventually they go from point A to point B. You go from point A to point B. You can go from point A to point B like human beings try to do the shortest path, like birds fly the shortest path. But think about a chloride ion sitting on the surface of a concrete bridge wanting to go inside. Does it have a straight path? No. The pore structure is tortuous, right? Does a chloride ion have an energy to drive through the concrete and go? No. It has the only energy the chloride ion has to go inside concrete is what? It's based on? What is that called? Concentration gradient, right? You have a higher concentration at one place, lower concentration in place. The same idea of water going from an area of higher pressure, higher elevation to a lower elevation. Here, higher concentration to lower concentration. Concentration is the only driver, and that driver is a very slow driver. So it has to find out the path through which it has to go to get to where it wants to get. So you have that percolation, which is never a straight path. Forest fires, have you seen pictures, satellite pictures of forest fires? Theoretically, you think it's such a dense forest, it started burning, it should go straight and burn through, right? Do you see that? It always goes in zigzag patterns. So, the algorithms that people write, computer software algorithms that people write to figure out how percolation is called the burning algorithm. Okay? It is like a fire that burns in a forest. It doesn't burn in a straight line. It burns and finds out the driest leaf, burns the driest leaf, gets more energy so that it can burn less dry leaves. Right? So, it will be going on searching for where that temperature gradient is to do that. Okay, so that's what I said here, forest fires. Epidemics. Recently we had in northern Kerala, Nipah virus. Yes, you guys all were very careful here. I even saw a notice outside, don't travel to Kerala, right outside the hall here. So, epidemics, travel, they gain percolation, right? Goes from one person to the other. Again, for that epidemics, how is he finding the person? It doesn't hit a healthy person, it hits a person whose immune system is weak. Basically, so if I am sitting next to a guy with a severe cold, I may not get the cold if my immune system is strong, but a guy sitting 4 rows behind might get the cold if the immune system is back, right? Again, percolation, not based on the nearest neighbor, but based on what is the most appropriate condition. So, remember this. It is the appropriate condition in any material. What determines the properties is the appropriateness of the condition, not essentially the nearest neighbor. Remember yesterday when I showed you nearest neighbors. So if I have one cement grain here and another cement grain here, and this cement is the nearest neighbor of that cement, but they need not talk to each other because this grain is saying, I don't need you. This grain is saying, yeah, neither do I. I can hydrate on my own. But if there is a limestone particle 10 microns away, both of them need that particle. See that? They are trying to look at the equilibrium. Can I get some carbonate ions from there rather than silica and alumina from this guy who is sitting next to me? Opportunistic. Every chemical reaction is opportunistic. It's not fair, based on fair practices, right? If it's fair, the guy sitting next to me should get what I have now, so that socialism, right? Reactions are not socialistic. Reactions are always opportunistic. And what drives the opportunism? You know that, I told you before. What drives this opportunism? My selfish desire to go down to a lower state of energy. Simple. If that principle is clear in your mind, you can explain pretty much any phenomena that happens in chemical reactions. Okay? Every system wants to go down. So percolation, trying to go through a path of least resistance, is because I don't want to spend energy. I want to have energy in the bank, like all of us do. Make money, save money, don't spend money, and then don't get a chance to use the money, right? That's the difference when you go to Western countries where, in the US, they typically say, recently they have started, they don't save money. Because here you save money to get your kids to school, right? They tell the kid, hey, if you want to go to school, go take a loan. Why do I care? Right? So they don't save money. They use money for what they want, which is actually a good thing. Sometimes I felt that, you do all these, and for all of us who are very Eastern civilization based, we spend a lot of time worrying about what will happen. We spend a lot of time thinking about all these, and by the time we are close to the end of our life, we realize that we haven't really lived. Right? You look at those people, they happily enjoy their life. I don't know if it's for good or bad, but you look like they have no problem. Yeah, kids go to school, yeah. If he studies well, he goes to school. What happens if he doesn't get a fellowship? Oh, if he doesn't get a fellowship, he'll take a loan. Who will pay the loan? He has to pay the loan. He has to finish college, work, pay the loan. So that's why a lot of students that we see work 2 jobs while they come to school. That's the difference that, again, trying to go off track, but just to give you some information. That's the difference. A lot of BTech undergraduate students that I have in my class are so responsible and mature. I don't have to tell them 10 times where is your homework, whatever. There are some slackers always. But a lot of these students are very mature because they are working 1 or 2 jobs while they are studying. They are making money to pay for the tuition. And remember, in the US, until 12th grade, 0 money spent by parents for kids to go to school. So I have to spend nothing to send my kids to school. Totally free. But then, when you want to go to college, they will extract all the money you saved from 0 through 12, plus all the interest at 25% for that year, plus some more. College is ridiculously expensive. So, if 1 year, just the tuition in an engineering school for 1 year, if you don't have a fellowship or a stipend or some kind of a scholarship, you're looking at just as tuition for a year, $25,000. So do your math. It's that expensive. So if you get scholarships, you can get 50% scholarship, 20% scholarships, whatever. So it's very expensive. So people do jobs, they take loans, they get low interest. Interest rates are really low in the US. So that's the first thing that struck me when I went there. Right here we say everything is an 8% loan, 9-10% loan. Their loans are 1%, 2%. So if you want to buy a house, you get 3-4% loans to buy a house. But again, there are downsides to that also. If you invest money in a bank, you get 0. Okay, you can put as much as you want in savings account or checking account or whatever. You almost get 0. No interest at all. So the only place that this is capitalism. The only place that you get interest is when you put money in the stock market. But then one day everything will go also. Right? So if you're willing to take the risk, again, you take more risk, you get more reward. So all our retirement money is in stock market. So I'm really worried, right? When I have to retire, if I have to retire, I don't have to retire, but if I can't work one day and I'm so ill and can't work, I have to retire eventually. And if I have to retire, at that time the stock market is crashed, I'll have nothing. So it's always this uncertain scenario that happens because all the money is in stock market. But now stock market is doing really, really well, so everybody's happy. If you see US economy, everybody says Trump is doing a good job. It's not because of Trump. He's not doing anything. He's actually doing bad things. But anyway, so fracture, concrete fracture. I'll talk a little bit about fracture and fracture mechanics tomorrow. Fracture also is a percolation process. You have one crack. That crack, have you ever seen, unless you do a very quick impact kind of loading, have you ever seen a straight crack in concrete? Crack goes around. Typically what the crack does? Crack tries to avoid the coarse aggregates, right? Because coarse aggregates are strong and dense. Crack goes around. Percolation of cracks. It's trying to find the path of least resistance. Corrosion, clustering, correlation. So we'll do all of that. We'll do a little bit of all of that. So percolation is analysis of clusters, their statistics and their properties. Okay, so just to give you a quick example of trying to find the boundary of these white particles, and you see how you can go from, see here, how you're tracking, how you can go from through the interface of black and white from this end through this end. See how tortuous the path is? Right? So this is typically how. So you have a cluster. Now, can you relate to this picture? This is what you have when you mix cement and water. Right? You have a lot of particles in a lot of water. Which means when you start off hydration, and if I have a boat, assume that cement hydration is happening in an ocean, and if I can have a boat when I start, when the cement is mixed with water, if I have a boat, from one end of the hydrating volume to the other end, I can completely go through water, right? Without touching any of those islands. But once the cement starts to set, it will start breaking off all these connections, right? You will start connecting all these particles together. At some point, so when you start off, your water is completely percolating. You see that? Your water is connected from one end to the other. 7 days later, your water is in isolated pockets. Your hydration products are connected from one end to the other. But there is water and there is some connection of water and there is some connectivity. But what you want in a percolating system with cement paste is the fact that after 7 days or whatever time, your percolation of cement hydration product should be so complete that water should not have a continuous path. Only if water has a continuous path will all your bad materials go in, right? None of what damages concrete damages the cement paste directly. They get dissolved in water in the pore solution, transport through that and then start all the problems, right? So there are different ways of doing. So you have a pore solution in concrete, right? Pore solution meaning the water with all these ions. So one of the ways, a smart way some people have done is to add some chemical to make this pore solution more viscous. So basically, okay, I know I cannot make the cement hydrate more. I know I will have all these pores and the pores will have pore solution. Okay, I will add some chemical to make this solution more viscous. What's the advantage? Can you swim faster in water or swim faster in honey? If I give you a pool of honey, will you be able to swim fast? No, why? Honey is very viscous. Same idea. The ions that are coming from outside trying to attack the concrete will have a lot of difficulty trying to swim through the viscous pore solution. Very smart idea. The problem? Something to make this concrete pore solution viscous is very expensive. It's very difficult to manufacture, very difficult to use. It has other issues. But people have successfully tried it. Very simple idea. I'm doing nothing but adding one more admixture to the series of things, and all this admixture does is to make the pore solution more viscous. See the idea? So see, kinds of different things that people do. So it's all based on the idea of percolation. So initially your percolating structure is like this. After some time, you see a little more connections here. When you get here, even more connections. When you get here, even more connections. Now you can actually start seeing here and going through and finding how do I go to the other end. See, if I come through here and go through here and squeeze through here, I'll get stuck here. So that path is closed. If I come through here, that path is closed. Through here, squeeze through here, go through here. I know, you can play around with this. You can use this as while you're traveling back, if you're traveling in a train or plane, use this to play around and find the path. Okay? So, you may not have a percolating path in this. It might have been completely blocked off. And this is what you want. Now, start reverse engineering. If this is what I want, what are the different options I can have to block this path off? Right? What happens if I have lot of fine particles? Faster blocking off? Right? Because lot of surface area, lot of volume gets filled, you can have finer particles. I can increase the degree of hydration, the rate of hydration, make cement react more, it will block the path off. I can start off with a higher volume of cement, which means lower water cement ratio, block the path off. Again, now you have a plethora of options that you can choose based on what kind of option you want. Okay, I'll skip this and I'll go to the next one. Okay, so you talk about a percolation threshold. Now, for a square 2D lattice, so if I take a square 2D lattice and I'm assuming that the percolation is only because of the bond between two particles, if I have 50% of particles randomly distributed in the system, I will have percolation. Okay? 50% by volume randomly distributed in 2D, I will have percolation. If it is 3D, mathematically you have to do some computer studies, and I'll show you some examples. Okay, so this is a 30% volume fraction. Can you see here? It's connected completely, right? I can go from here to here completely. See here? Right? When you get to 50%, most of my paths are blocked. I don't think I can go from this side to this side. See that? So 50% is roughly in 2D the percolation threshold. In 3D, so you can see here red and white, red connected, white disconnected, red partially connected, white partially disconnected, red partially disconnected, white partially connected, red disconnected, white connected. Red connect, white disconnect to red disconnect, white connect. So consider red as solids, red as water, white as cement grains here. Right? That's what you start off. Right? Water connected, cement disconnected. You end with water disconnected red or